Greetings and welcome, friends. We're today talking about inductive and deductive reasoning, and just a lot more logic that we're going to be looking at today. It says inductive reasoning. First of all, it defines what a conjecture is. A conjecture is an unproven statement based on observations. So in the world of science, what would we call a conjecture? A hypothesis in the world of science is what we would call a conjecture in the world of logic. All right. Whereas in the world of logic, a hypothesis is the initial statement in an if-then conditional statement, right? So let's see. It says you can use inductive reasoning when you find a pattern. So here's the key. Inductive means pattern in specific cases, and then write a conjecture for the general case. So you follow a pattern and then come up with a hypothesis. I almost said theory there, but so let's see. Describing a visual pattern. So describe how to sketch the fourth pattern in the figure and then sketch the fourth figure. We could do this in the opposite order if it helps, but yeah, does anyone have a way to describe it? Ryan. So let's see. So originally I had 2 parts, then 4 parts, then 6 parts. Okay, which is valid because, yeah, I might have expected this to be exponents here. 2, 4, 8, 16. So I'm expecting it to be 8. So so basically divide the circle into the next even number of parts. I don't know. Maybe that's not the prettiest way to describe it. Into the next even number of slices of sectors. And then how do I determine which one to shade? Is it? This one shaded the top half. This one shaded the top left half. And then it looks like this one shaded, yeah, top left half. But we're going to have a somewhat of a dilemma in this next one. Our pattern is insufficient to make a full conclusion. But I'm expecting, right, I'm going to divide this into 8 sectors. Because now I've got a tie between left and top. Yeah, do I want to shade here or here? So you guys are arguing too. That's what I'm leaning towards as well. But yeah, I think it's that one. So shade the left topmost sector. The most left top sector? I don't know. Clearly I'm a mathematician and not a word-matician. Is that what they call those people that use words? Probably a word-matician. Yeah. So I also have like monitoring progress questions, kind of 2 and 3, if you want to take a look at those for fun later. Let's talk about conjectures though in a mathematical sense. Although I guess these figures are still described somewhat mathematically. So let's see, making and testing a conjecture. The numbers 3, 4, and 5 are called consecutive integers. So consecutive, what's another way you might describe consecutive? Like if we were talking to like an elementary schooler. In a row, right? They're like one after another. They're next to each other. Yeah, I like it. I like it. Make and test a conjecture about the sum of any 3 consecutive integers. So I guess I'm going to have to come up with a way to describe consecutive integers. So the first one I could call x. What would the next consecutive integer be if my first one was x? I could call it y, but it might be more helpful to define it in terms of my first one. How far is 4 from 3 or 5 from? Yeah, so x plus 1. And then 5 was how far from the first one? Yeah, 2. So x plus 1, and x plus 2 is going to be how I describe 3 consecutive integers, and then I'm going to try to make a theory about the sum of them. So I'm going to say x plus 1 plus x plus 2, and I think I could simplify this. I mean, there's a bunch of different ways. I could probably say it's going to be an integer. It's not going to somehow become a decimal, right? Integers are basically non-decimal. 0 is cool, negative is cool, that sort of thing. So let's simplify this. X plus x is 3x, and then I could combine. I'll show that a little bit prettier. X plus x was 3x, and then how about 1 plus 2 is 3. And then I could try to come up with some statement about this. You know what I'm going to say? I don't know if you guys realize this. I'm going to claim it's divisible by 3. I think that's an interesting claim. I could also claim it is an integer. Is an integer. Right? So those are some claims that I could make. Any other interesting or obvious claims we could make? Do you guys spot something different? Yeah, Emmett? Oh, like you used these values? Okay. Oh, okay. I like that. So this was equal to 9, and then 3 plus 4. And so our goal is to describe any 3 consecutive, but starting with actual numbers isn't a bad idea in case you can recognize a pattern. So this would have been 12. And so you recognized that this number is what? The sum of, or sorry, something about the middle number? Okay, so if I take this and divide by 3, that this should then equal the second number. Yeah, I think so. So that's an interesting conclusion. Someone could reword that and say triple the second number. Right? And then they asked to test it, and our testing of it is literally then pick some numbers and see if you can prove your thing wrong. So yeah, so there's a bunch of different claims you can make. So I don't know, let's just try a test. How about like 10 plus 11 plus 12? So that's going to be what, 33. And is that divisible by 3? Yeah. Is it an integer? Yeah. Is it triple the second number? Yeah. Is this divided by 3 equal to the second number? Yeah. Now, what's interesting here is by testing it, I haven't proven my conjecture. I haven't guaranteed its truth. And I could run tests I could run infinitely many tests for the rest of my life and still not prove that it's true, because it only takes one falsehood to disprove my conjecture. Isn't that like, I don't know, is that like scary or sad? Like, yeah, does that mean anything's ever proven? Interesting. Right, I've got to prove it for everything. So right now it's just a conjecture we made. But to show a conjecture is true, you must show that it is true for all cases. And so how do you do infinitely many cases? That's an interesting challenge mathematically. You can show that a conjecture is false, however, by finding just one counterexample, right? Talk about, right, throwing a wrench in someone's, I don't know how to finish this analogy. Whatever. And a counterexample is a specific case for which the conjecture is false. So we can disprove any claim with a single counterexample. And then mathematicians have found a variety of ways of proving things true for all cases. Now, actually, maybe I was foreshadowing a little bit too much, but even this way, even the fact that I was using generic versions, I kind of could have proven my divisibility by 3, right? If I divide this by 3, I would have had x plus 1, which is an integer, and therefore it's divisible by 3. So, like, you can prove it by doing generic cases rather than specific cases. And then there's some really interesting logical approaches to proving something true for all possible cases. All right, but logically speaking, when you're using a pattern, what's it called? Inductive reasoning, and then, yeah, making a conjecture is like that. So let's see. Let's find a counterexample for this. A student makes the following conjecture about the sum of two numbers. Find a counterexample. Oh, yeah, let's ruin this kid's day. I can't wait. Well, I'm sorry. I guess I can wait. And then I'll ruin their day. Here we go. So let's see. The sum of two numbers is always more than the greater number. That might feel true-ish. All right, 2 plus 3 is 5. This is bigger than, right? 5 is greater than 3, sure. But yeah, you found a counterexample. You said, what was yours, Emmett? 1 plus negative 2 is negative 1. And is negative 1 greater than, which one's the bigger number here? The 1, yep. And that is not true. And so finding counterexamples, the classic things you'd want to test would be like 0, negatives, right? Those are really the classics, because negatives would break things, anything talking about like square roots or an even root. Yeah, like in terms of picking numbers, those are the ones you'd want to find, like so. So yeah, so this is a counterexample. So 1 and negative 2 were a counterexample to this student's claim. And then finding a counterexample doesn't actually necessarily ruin your day. It might allow you to then revise your conjecture. You might be like, oh, so any two maybe positive numbers. But then I might ask, does 0 still work for this? Unless they're both 0, right? Then it's not greater than, but I guess there is no greater number there either. But yeah, so I might be able to say positive numbers or maybe non-negative numbers if they're distinct numbers, right? There's a bunch of different ways that you could kind of make that claim. So a different kind of reasoning, which is stronger reasoning than following a pattern, right? Because, right, patterns can be broken. Like, actually, I was watching a Neil deGrasse Tyson video the other day about, like, you know, like the phrase "what goes up must come down" is a pattern-based claim that is false, right? Because we've sent objects into space that are never coming back to Earth, right? They've gone up and they are not coming back down. But it was still like a pretty helpful conjecture for a while to describe a vast majority of objects, right? So like and then you can refine it, and it's great. But deductive reasoning is more powerful. It uses facts, definitions, accepted properties, and laws of logic to form a logical argument. This is different than inductive reasoning, which used specific examples and patterns to form a conjecture. And here's two, count them, two laws of logic. All right, and we're going to analyze both of these. So this says this. This is actually an if-then statement about if-then statements, which is just like, this is like inception of logic here. Here you go. So let's see, if, then, so check this out. Let's see if I can figure this out. If P, did I give myself enough space? Maybe I didn't. Let's say I said if P implies Q is true. Let's see if I can write this out. If P implies Q is true, so if a true conditional statement is true, all right, and P is true, okay, so and its hypothesis is true, then what is true? If P implies Q is true, and I know that P is true, I've already picked the color, then you know that Q is true. Okay? So if I know the conditional statement and it's kind of prerequisite to apply the implies, yes, wow, then I can conclude the conclusion. All right, that's called the law of detachment. That's just like, this is how if-then statements work. All right, but it requires two pieces. If you only know the if-then statement is true, I don't know that Q is true. Right, like the if today is Wednesday, then yesterday was Tuesday logic. That is a true conditional statement, but I can't conclude that that yesterday was Tuesday until I also know that the hypothesis was true. All right, this next one, law of syllogism, is a little bit trickier. It says if, let's see if I can quickly write all these colors down. If P implies Q, let's see, I'm gonna just save time on the yellow there. So if P implies Q and Q implies some other fact, T or R, they used R, didn't they? They used R. R, then what do you think is true? Right, then P is going to imply R. Does that mean R is true? Not necessarily. All right, notice, right, I've got two things that are true, and this is kind of, I call this like the transitive property of logic. Right, the transitive property in equality was if A equals B and B equals C, then A equals C. You can kind of connect those two middle things. Right, if P implies Q and then Q implies R, then I can let's just skip the middleman, right? Let's just skip this and just say, oh, P implies R. So what this is, the conclusion here is an if-then statement, not a statement. So I don't know if R is true until I also know that P was true or that Q was true. Okay? So I don't know whether or not R is true. I just know that this if-then statement is true. So those are kind of like the two laws of logic, and you're going to then kind of apply them and use them and describe them and determine whether or not they work for a particular situation. Yeah. I hope my explanations are helpful. I'm trying. I'm like swinging for the fences here. So if two segments have the same length, they are congruent. You know that BC is equal to XY. Using the law of detachment, what statement can you make? So let's see. I have if I've got P implies Q is true. Right? And then what did they tell me? I also know this. What statement is that equivalent to? Is that P or Q here? Two segments having the same length. That's the same as P. So using the law of detachment, what statement can I make? I can conclude Q. If I know P implies Q and I know P, then I can conclude Q. And for us, I would say BC is congruent to XY. Yeah. It's just applying the if-then logic. Now, what if I had the same thing? Well, actually, no, never mind. That's a poor example in this case. A false law of detachment would be this. If P implies Q and Q is true. All right, sometimes people might try to combine these and say then P is true. But this is a false claim. This will fail you. Right? I can't start at the conclusion and end at the hypothesis unless it's biconditional. And I was going to write that about this, except in this case, this is biconditional. If I started with this, I actually could have concluded that by definition of congruence. But yeah. So there you go. Let's use the law of syllogism. And then you can even sometimes apply both of these if you know a whole bunch of facts. And how wonderful would that be if I knew a bunch of facts? I know a bunch of facts. Hooray. I imagine I could like have an awesome musical where I sing about the facts I know and applying logic. Maybe someday I will. Let's see, if possible, use the law of syllogism. So that's the transitive property. So here it says, if x squared is greater than 25, then x squared is greater than 20. Okay? I also know, so notice these are two if-then statements. I don't actually know this, I don't know, I don't know this, I don't know this, I don't know that, I don't know that. All I know is these two if-then statements, okay? So it says, if x squared is greater than 5, then x squared is greater than 20. And then it says, if x is greater than 5, then x squared is greater than 25. Is there any way I could combine these? I need the conclusion of one to be the same as the hypothesis of another. And look at this. Let me color code it for us. So I've got P and Q here, and then Q and R here. They gave it to us in the opposite order. You guys catch that? So because this, I'll circle them in blue. Here we go. Right, because this and this were the same, I can skip the middleman and just say, oh, therefore this. You guys, are you feeling it, Mr. Krabs? Yeah? So if x is greater than 5, then x squared is greater than 20, is what I can conclude. I don't actually know x is greater than 5. I just know that this statement is true. All right, how about this one? If a polygon is regular, then all angles in the interior of the polygon are congruent. And this says, if a polygon is regular, then all its sides are congruent. So notice this. I've got if P, I've got if P implies Q, and then I've got if P implies R. Can I apply the law of syllogism here? No. I never have the conclusion of one of these being equivalent to the hypothesis of the other. So I can't combine them. Basically, all they've given me is this. They says P implies Q and P implies R. But I don't have a chain where I have like a P implies Q implies R. Therefore, P implies R. I don't have that chain. Right? So it's basically you need this to equal that, or I would have needed this to equal that to be able to combine those. All right, like this is like true and helpful information. It just doesn't use the law of syllogism. All right. Because it gave us an example where it was working and where it wasn't working, and you had to, if possible, determine whether it applies. So that's the challenge, right? I'm teaching you properties of logic, and then you've got to figure out, can you use them in the situation you find yourself in? This, I don't even remember where I found this problem. I don't know why it's called example 1 again, but I like this problem. It says the syllogisms below represent common types of flawed reasoning. So here's brokenness, okay? Explain why each conclusion is not valid. So let's see. When it rains, the ground gets wet. I'll try to label these with P's and Q's. So if it's raining, the ground is wet. I then know that the ground is wet. Actually, I heard this exact example in a science book I was just listening to last month. Therefore, it must have rained. So they ended up just applying Q implies P. And that is not true. I can't apply the law of syllogism here. And could you actually think of a counterexample? A sprinkler, another one. A hose. Morning dew. Wow. Right? A flood. Yeah. An earthquake that opened a channel to the ocean. Urine? Yes. Okay. Some sort of like post Super Bowl parade with millions on the streets in the city of Boston, and them not applying appropriate hygiene in where they choose to urinate. Yes. Very good case. Very good real world situation we might be hearing about today. Let's see. How about this? If triangle ABC is equilateral, all right, so there's a P statement, then it is isosceles. There's a Q. And then they just said triangle ABC is not equilateral. How could I describe that? Not P. Almost there. Not P. Therefore, it must not be isosceles. Not Q. So this, we could describe what that's the inverse, right? I believe, of the original statement. And I don't know the inverse is true just because I know the original is true. This logic only works when I have the P, not the not P. Not the not P. All right? Very good. Okay. So that one fails. Let's see. All squares are polygons. So if it's a square, then it is a polygon. All trapezoids are quadrilaterals. All right? That new information. We'll call that R, all trapezoids. If it is a trapezoid, then it is a quadrilateral. We'll call that S. Therefore, all squares are quadrilaterals. Now, that might be a true statement, but if all I knew was these two, I cannot conclude that. Because none of the conclusions were the same as the hypothesis of the other statement. All right, so I agree all squares are quadrilaterals is itself a true statement, but it is not true because of the combination of these two statements. All right, so that's weird, right? It's a little weird. No triangles are quadrilaterals. So if a shape is a triangle, then it is not a quadrilateral. Or I guess, I don't know, I'm going to call that not Q. So my Q statement is not quadrilateral. Yeah, I don't know. Some quadrilaterals are not squares, so here's Q. So is quadrilateral, and they're saying some quadrilaterals are not squares. So some Qs are not squares. So you get a better tilde there. Therefore, some squares are not triangles. Yeah, this is just like all over the place. And it might be some true statements here, but I never have a conclusion matching up to a hypothesis of the other statement. Yeah. Wow, that is interesting. Let's see, I think I'm going to call it. And then I want to do an activity with you guys. So, goodbye, internet friends. You can figure out the rest on your own.